Right. So the next section in the first unit is Sylow's theorem. It's a partial converse to our Lagrange's theorem. You know that Lagrange's theorem states that if G is a finite group, and H is a subgroup of G, then order of H divides order of G. So this is our Lagrange's theorem. Lagrange's theorem states that if G is a finite group and H is a subgroup of G, then order of the order of H divides order of G. So what will be the converse of this? You would have studied even that. If there is a number, see, suppose I have, say, order of G to be, say, some number n. Suppose I have order of G to be, say, some number n, and suppose m is a number which divides n. Question now is, can I have G? Can G have a subgroup of order m? Here I know what is order of H, G finite. So, I mean, H is known, order of H definitely divides order of G, that is Lagrange's theorem. Converse is, do I have, suppose I have, see, for example, if I have 12 to be a number, okay, which is order of some group, say. Actually, converse is not true, we will be considering A4, alternating group, which is a subgroup of S4, collection of all permutations on 4 symbols. So in that A4 is normal. So order of A for collection of all even permutations. There is another name given to this A4, that is alternating group. So 6 is a number which divides 12, very obvious. But A4 does not have, this A4 does not have any subgroup H which is of order 6. So which is of order 6. So that means converse of Lagrange's theorem in general is not true. So then what is this Sylow's theorem? It says that partial converse to Lagrange's theorem is true. That is, suppose I have order of, see, given any number, we know that it can be written as product of prime powers. So if P power alpha divides order of G, then G has a subgroup of order P power alpha. See here, this number is not power of a prime. It is 2 into 3. It is only product of primes. Okay, even though any number can be written as this, you can write as 2 square into 3. So had I had 2 square dividing, if this is the case, definitely I can say that my A4 has a subgroup of order 4. And even 3 divides this. So I can definitely say that this A4 has a subgroup of order 3. So, but this is not true. Then what could be the generalization of that? So for that only the Sylow's theorem, there are 3 parts in that Sylow's theorem. First we are going to see the first part of Sylow's theorem, which states that if G is a finite group of order, say some order of G, and P per alpha is power of a prime number, P is a prime number which divides order of G, then G has a subgroup of order P per alpha. So that is what we are going to prove in Sylow's theorem. So before we prove Sylow's theorem, we need to have certain facts. In order to prove the theorem, we will be using these facts. The first one is this. That is, this is simple. All of you know it. Suppose I have G consisting of only 3 elements. Then script P of G, that is the collection of all subsets of G. Empty set is a subset. The set itself is a subset of itself, and the set which consists of only 1 element, and then 2 elements. So everything we have listed, and you know already that if G has 3 elements, then script P of G, the collection of all subsets of G, has 2 cube elements. So that is known to you. Any set which has 3 elements means the collection of all subsets has 2 cube elements. So now what we want to find out is how many subsets can have only 1 element. So in this case, we have only 3 sets having only one element. So the number of one element subsets is 3, which we can write as 3C1. This we need, that is why we are writing like this. And number of two element subset. So that is again 1, 2, 3, 3 only we have. Then how that is interpreted here? 3C2, right? And then number of three element subsets. So we have only three element subsets to be just one. So you have one. How that is interpreted? It is interpreted as 3C3, right? So in the same way, if we have G consisting of four elements, okay, then the subsets with just one element, we have just singleton 1, singleton 2, singleton 3, singleton 4. And how many such subsets that we have? 4. How that is interpreted? 4C1. And then two element subsets. We can have 1, 2, 1, 3, 1, 4, and then 2, 3, 2, 4, 3, 4. So all that we have listed. So how many there in number? We have the number of two element subsets is 6. How that is interpreted? 4C2. So in the same way, number of three element subsets when you find, you will have that to be 4. So how that 4 can be interpreted? 4C3. So from these two, what we conclude is, if I have G consisting of three elements, if G has three elements, if we want one element subset, it is 3C1. N is here, G is the set which has n elements in general. So in that case, I will have NC1. The number of two element subsets will be NC2 and NC3 in the case of three elements. In the same way, just apply that, that will be true even here. So 4 means 4C1, one element. Number of elements in G is 4. I want to have two elements in each subset. So number is 4C2. So like this, in general, if we have, if G is a group of order n, if G is a group of order n, then the order of collection of subsets, you collect all the subset that consist of, so in this we have each one consisting of k elements. There what we did, two elements, one element, three elements, like that. So here each subset has k elements. So like that, how many such elements will be available? So that is the order of this collection. So order of a collection of subsets of G having k elements. What is the group order? It is n. So naturally, by the above argument, we can conclude that it is NCK. So how many such k subsets will be available? It is NCK. This NCK, we have got another notation. What is given here? Okay, you have to. You can also write your NCK in this way. Right. Now, the another argument, what does it say? If P power R divides M and P power R plus 1 does not divide. So you have, see, when you write divides, we have to dividing 6. So you are supposed to write this straight line. No, I mean, it should not deviate like this or like this. You are not supposed to write 2 divide 6 means this is the correct notation. Straight line should be there. And this I am not able to, but straight line A divides B means A, straight line. So like this only it has to be written. All these are wrong. It should not deviate. It should be just a straight line, right? So if P power R divides M and P power R plus 1 does not divide M, then what we want to conclude is P power R will divide MP power alpha, C P power alpha, and P power R plus 1 does not divide. So even here it does not divide. In some book like this they would have denoted, in some this. So that doesn't matter, does not divide. Okay? You can use like this or like this. So that doesn't matter. So what does it say is, how your M behaves, in the same way your MP per alpha, CP per alpha behaves. How M behaves? M is divisible by P per R. M is not divisible by P per R plus 1 means M P power alpha, C P power alpha is divisible by P per R, and M P power alpha, C P power alpha is not divisible by P per R plus 1. So how your M behaves, in the same way only your MP power alpha, CB power alpha behaves. So that is what is established in this second fact. So we know that NCR, you know that NCR is given by n factorial NCR is given by n factorial divided by r factorial into n minus r factorial. So it is this that we can use, and of course either one we can further simplify. You can write it as n into n minus 1 and so on up to 1. But before to that we can have, see, I can have n minus r minus 1 and so on. So when you and then simplify this, so you can cancel, see this will be your n minus r factorial. So from that term onwards, whatever is present that you will be writing here. So the final, this NCR, which is n factorial by r factorial into n minus r factorial, the concept that what we have, that the same thing that we are using here. So you have, you suppose I treat this as my n say, and this as say r, what here we have is this n minus 1 and so on and so on. You have n minus r minus 1, right? And then in the denominator what we have is r minus 1 and so on up to 1 you have. So this n minus r and the remaining, so whatever here I have, no, that term will get cancelled with this r factorial remains as such, and n minus r factorial here. So these terms will get cancelled with this. So what remains is only this in the case of NCR, and in the place of n I have MP power alpha, in the place of p power alpha I have r. So this is, because of this becomes like this, right? Now the question, we want to say that how my m behaves in the same way this one is going to behave. So that is our claim here. How my m behaves in the same way this one is also going to behave. So how that is established? If at all there is any factor, see in p power alpha minus I, this is a term in the denominator, randomly that we can, I mean generally we will pick so that it can be applied to any of the number over here. So we consider p power alpha minus I. So suppose I have this one having some factor, right? See, if it is like this, then obviously there is, you don't have any factor common to them. This is different means naturally. However, my m behaves in the same way, this one will also behave. So in that way, the claim can be established. In case we have some common factor, so suppose I take my p power s to be a factor of p power alpha minus I. Suppose I have p power alpha minus p power s to be a factor of this one. This is going to be some number in that I have p power s to be a factor, say, because any number we can write that as a product of prime factors. So suppose p power s is a factor of this. That is p power s divides p power alpha minus I. Then we can write, you know this, a divides b means b is written as integer times a. So that is known to you already. So using that I can write my p power alpha minus I as some integer times p power s. So straight line divides, straight line should be used. So this is what we have. So from here I is, you take this to the right side and bring this one to the left. So I is this, you have I to be this, let it be. Now we shall consider the corresponding factor over here. All right. So what we are going to say is, if they don't have any common factors, well, very obviously my m and this one will behave as such. Suppose I have generally this term having a factor p power s, what we are going to show is corresponding term over here will also have p power s as a factor. So if that is the case, then they will get cancelled. So now again, what will happen? My m and this one will behave as mentioned earlier. right? So my I is this, right? Now, if P par R divides M, P par R plus 1 does not divide M. So this is what we are trying to prove. That is again written here for continuity. That is written here. So I have I is equal to P par alpha. This is what we had. Just now we had in the previous page. So this is what we have. You consider this factor M P par alpha minus I. Now what we are going to do, replace our I by P par alpha minus L P par S. So you replace this one, and so this is minus into minus plus. So you have L P par S, and then plus. In from these two you take P par alpha out. So what you are left with is M minus 1. And now you take P par S outside, so that L will be here, and here it will be P par alpha minus S into M minus 1. So this is going to be some number. This one is going to be some number. So what is my conclusion when I have? So this would imply that my P par S divides M P par alpha minus I. Isn't it? So what I assumed here, let P par S be a factor of P par alpha minus I. So for this, I assumed P par S to be a factor. And what I have got from this one, P par S is a factor of this. So likewise, for each one, I can have factors if at all. If they don't have, well, there ends the matter. If at all they have, correspondingly, they should have the same factors, which means I can cancel them. So I'll be left with, so all this will now be free from P. In the sense, you will not have any P factor at all. So because of this argument. So which means what? If my P par R divides M means my P par R will also divide this. And if my P par R plus 1 does not divide M means it will depend, the whole lot will depend only on this, because this is going to be some constant, some number which is free from prime factors. So naturally, as my M behaves, my MP par alpha, CP par alpha will behave. So this is the thing that we are going to use in the proof of the first part of the Sylow's theorem. So what does first part of Sylow's theorem say? If P is a prime number and P par alpha divides order of G, then G has a subgroup of order P par alpha. So a number divides. What previously we said, if any number divides order of G, then G need not have a subgroup. That is converse of Lagrange's theorem, which is not true. But what is given here? It is a power of a prime number. If that divides order of G, then G has a subgroup of order P par alpha. So this subgroup only we are going to later give the definition, that is called the Sylow subgroup, P Sylow subgroup. The name given to this subgroup. Such a subgroup will always exist, and that is called P Sylow subgroup. So how are we going to prove the theorem? We are going to make use of the equivalence relation technique, and the technique, I mean, what we have used here, what we just proved, no, even that first that we are going to use, and we will be introducing one H. So this is the required H that we'll be claiming. First, we will prove that it's a subgroup, and the one what we proved in this theorem, order of C of A. Before we established the class equation, we proved that order of C of A is equal to order of G by order of N of A. The same technique that we are going to use, so that we established by showing that there exists a one-to-one correspondence between C of A and G over N of A. So the number of elements should be the same. Same technique that we are going to adopt here to prove that there exists a one-to-one correspondence between these two. When it comes, we will have in detail. And the last claim will be the H, that what we introduced here is the required subgroup, which will be of order P par alpha. So that is how we are going to give the proof of this theorem. This is the out sketch of the proof. You consider script M, that is in a group G. What is first happening? My P par alpha divides order of G. right? So if P per alpha divides order of G means I can write order of G as some m times P per alpha. I can write order of G as this. So in this I have m P per alpha elements present in G, right? So we are going to consider those P per alpha elements, those subsets, not even subgroup. So just subsets which consist of only P per alpha elements. This one will have P per alpha elements, this one will have P per alpha elements, this one will have P per alpha elements, like that. So you may think that if you have order of G to be m into P per alpha, there will be just m P per alpha subsets only. But there is no guarantee for that. The reason is I can have m and P to be relatively prime, or they are not relatively prime. So if they are not relatively prime, then by just looking at order of G as m P per alpha, we cannot come to a conclusion that there can only be m number of such P per alpha subsets. So that we cannot conclude. So that this is the first case that we will consider, and in the remark, we will be discussing that what will happen when m and P are relatively prime. So that is given as remark, and this one. So this is what your script M is. You collect all this. So this is my script M. Everything is happening in G. What is G? G is a finite group. What do I know about G? P per alpha divides order of G, which means order of G is m into P per alpha. So first, what do? I consider all the subsets of only subsets of G, which consist of P per alpha, and put that collection and name it as script M, because each one being a subset, we'll have to use only script M. So script M is the collection of all subsets of G having P per alpha elements. So then we discussed, if I consider the set consisting of K elements, you have all the subsets having K elements means, then what is the order of this? What is the order of this collection? It will be NCK. It will be NCK, right? So